decomposition with inverse trig functions. Now normally in algebra we think of an inverse function as being one that undoes the original function. So these three proposed statements that I have on the screen would seem reasonable. If you applied the inverse sign to a value x and then applied the sign, from our study of algebra we would guess that those would cancel out and the result would just be x. But notice I do have a question mark next to each of these. The fact is it turns out to be a little bit trickier than that. The answer may not be as simple as x, and that's one of those things that you'll understand much better when this video is over. Now it's important that you have already watched my inverse trig functions video or you'll have trouble following along with this one. So I've given an example here where we're taking the cosine of the inverse cosine of 1/2. Now again, intuition suggests that these two functions being inverses should cancel out and that we should have an answer equal to just 1/2. Let's analyze this problem and see if that happens or not. Now here's how we'll do it. Oh, by the way, you see I've reproduced the first and second quadrant because we know when we're dealing with inverse cosine that is what I refer to as being the search region for that function. Okay, so here's what we're going to do. We'll first have a look at the inner function, inverse cosine of 1/2. Now in the last video we looked at that and we know that we are searching within our search space here for an x value equal to 1/2, which we definitely find right here in quadrant 1 corresponding to an angle of pi over 3. So the inverse cosine of 1/2 is that angle, pi over 3. Well, now we can easily enough finish this problem. Now it's just what's the cosine of pi over 3? Well, it's kind of the reverse of what we just did, isn't it? We find pi over 3. We pick out the cosine, which is the x value there, and that's equal to 1/2. Okay, so it turns out that our intuition that the functions cancel each other is correct in this problem. But let's have a look at another one. Here we have the cosine of the inverse cosine of 2. Now, if we compare it to the last problem, we might think, oh, the answer is just 2. Dispense with all the work. Well, there we'd run into a little bit of trouble, and watch and see why that is the case. We would first work out the inner function, inverse cosine of 2. So we're looking for the angle that has a cosine equal to 2. Now we clearly don't find any coordinates where that happens. You might wonder, well, maybe it happens at some other angle not specified. Well, that cannot be the case because 2 is simply too large. Remember, we're looking at a unit circle here, and a unit circle means that the radius equals 1. So the largest any of those coordinates can be is 1. 2 is simply too large. So this problem can't even be solved. It is simply undefined. Easy enough to see it when you get into the logic of it, but you wouldn't want to just blindly look at those functions and go, oh, they cancel and the answer is 2. You'd be wrong in this problem. Now we're going to look at a very similar problem, but please notice that the first function in each case is the inverse sine, inverse cosine, whatever, and the inner function is just the regular trig function. This is the reverse of what we were looking at a moment ago. Well, again, algebra would suggest that the answer should be equal to x, but you should know from the previous problems that sometimes it's a bit more complicated than that. So let's look at an example of this situation. So I have the inverse function on the outside, inverse sine. On the inside I have sine of pi over 3. So let's just start with our working hypothesis. We think the answer will be pi over 3, but let's see if that turns out to really be the case or not. So here's what we do. We would first work out the inside function here. Okay? We'll leave the outside function for next. So working out the inside function, what is the sine of pi over 3? So we look for the angle pi over 3. We find it easily enough here. And the sine value of pi over 3, remember sine is the y value, so that would be the square root of 3 over 2. Let me remind you quickly again, the reason I have only the first and the fourth quadrants drawn is when we're working with inverse sine. Those are what I refer to as being our search regions. So now we're looking for the inverse sine of square root of 3 over 2. So you look at this circle, this half circle, and you're looking for, notice, a y value equal to square root of 3 over 2, because y would correspond to the sine. So square root of 3 over 2, let's find that. Well, there it is in quadrant 1, and the inverse sine's just supposed to tell you what the angle is. Well, sure enough, the angle is pi over 3. Okay, now that one seemed to work out perfectly, didn't it? We were just left with the pi over 3, that is, the inverse functions cancel each other out. Now, it's not always that easy. Let me show you what else can happen. You'll see it in this next example. Inverse sine of the sine of 2 pi over 3. All right, so first we have to do this part inside. So we'll have the inverse sine, whatever that inner function turns out to be. Sine of 2 pi over 3. Well, I guess we'd have to extend this circle a bit to find 2 pi over 3. 2 pi over 3 would be like approximately there. Okay, this is fine because we're not doing an inverse sine. The inner function is a sine, so we can look anywhere. And we have the sine of 2 pi over 3. Well, those coordinates there are negative 1/2 and square root of 3 over 2. So the sine of 2 pi over 3 would be equal to the y value, square root of 3 over 2. But now, for the inverse sine, that's where we truly have to stay within quadrant 1 and 4. So let's look for a y value equal to square root of 3 over 2. The only place we find that is here in quadrant 1. I've circled it. And what is that angle? That is pi over 3. So this is pi over 3. If you compare to the original problem, notice the answer doesn't turn out to be 2 pi over 3 because it's not within our search region for inverse sine. So does this make it difficult to do these problems? No, it just suggests, as I've shown you, that rather than making a hasty answer, you should analyze it step by step. It really doesn't take that long, and the important thing is you'll do these correctly. Here, one more example we're going to finish up with, and this is kind of a fun one. Now, yes, it is tricky, but we'll be using a lot of knowledge that we've already obtained. We're doing the cosine of the inverse tangent of 4/3, and I could go and change those functions to other things. The main thing is I wanted the inner one to be an inverse, but the outer one to be a function which didn't correspond to that inverse. So it's not tangent inverse. All right, so a little bit tough here. But once you see how to do this one, you'll be able to do similar ones. I'm going to use a technique in mathematics called substitution. I'm going to take this whole thing inside, and I'm going to just refer to that as being theta. Okay, so theta, in other words, equals that statement inside, the inverse tangent of 4/3. Now what that does is that means we can rewrite our original problem as cosine of theta. And that's the problem we're eventually going to solve. Now we can't ignore what I have written here in red. That's actually where the heart of the problem is, where the work is going to occur. Now here's what I'm going to do. I'm going to take the tangent on the left and the right hand side of this substitution. So if I take the tangent on the left, I'll have tangent of theta. If I take it on the right, I'll just have 4/3. The tangent, the inverse tangent, gone. So tangent equals 4/3. I'm now going to try to draw that situation. Now the tangent is positive either in quadrant 1 or 3, but since this originally started out as an inverse tangent problem, will be in quadrant 1 here. So let's just draw a triangle. It may not be accurate exactly in terms of the angle or anything, but this will be theta. And since we have tangent of theta equals 4/3, remember that from SOHCAHTOA, tangent is opposite over adjacent. So the opposite is 4 and the adjacent is 3. And of course we have a right triangle there since we dropped that vertical down. Let's use the Pythagorean theorem to find the hypotenuse. C squared would equal 3 squared plus 4 squared. That's 9 plus 16, which is 25. So C would equal 5. I'll go and I'll put it on the diagram. So we have a 3, 4, 5 triangle. Now stop doing this work. Now that we have the triangle worked out, look back at that original problem. It's asking what is the cosine of theta. Look at our picture. You can answer that question. Where theta is, the cosine would be the adjacent, which is 3, over the hypotenuse, which is 5. So the whole trick to doing this problem, and ones that are similar to it, is simply to do a substitution theta for the inner expression, and then you can use right triangle trigonometry to work that out. All right, signing out. Good luck to you all.